Well, good evening. I'm Charles Schultz, and this is the Randomizer. And tonight's subject is going to be magneto-optical. Now, that's an odd term, and it refers to materials that, under the influence of a magnetic field, change how light passes through them. And there are a number of materials that will do this, very unusual materials in some cases. And this all goes back to Michael Faraday, one of the greatest chemists and scientists that lived. And he also experimented a lot in electricity. He built the first electric motor, as a matter of fact, and optical effects used in storing data in computers. So all of this is tied together in interesting ways, and we're going to discuss that very shortly. Meanwhile, I'd like to remind you to go to schultzlaboratories.com or universesciencecenter.com and sign up as a member and help us develop more galleries, more exhibits, and more interactive content. If you wish to teach and you have some expertise that you think the world would benefit from, then join us. Talk to us. Let's see if we can't put together some virtual display house for you, a studio of some sort, where you can show all of your works, a gallery, let's say. It would be a great place to place your works out in the world so people can walk around and look at them and see what it's all about. And you can set up a classroom and share your expertise with them in live classes. You can reach people all over the world very easily this way. And it is a virtual world, so you can put a headset on and walk around as if you're in it. So if you've got an Oculus, a Vive, or even a generic headset, doesn't even matter. It doesn't have to be a name brand. Walk around inside, have fun, see what's available. Meanwhile, the Randomizer is live every 6 p.m. weekdays Eastern Standard Time, and also we pick a random subject for every episode of the Randomizer out of the hat full of over 1,600 or 1,200 or some amazing number of concepts. And that random concept is the topic of the day. Also join us for our robotics classes, 9 p.m. Eastern Standard Time on Mondays. Lesson 3 is tonight at 9. And I think that you'll really enjoy what we're sharing with you. Soldering, assembly techniques, programming, types of processors, sensors, all kinds of really cool stuff if you're interested in the art of robotics. So let's get down to the subject matter at hand, magneto-optical. So what does this describe? Well, imagine if you had a piece of glass that light would go through it in one direction, but it would not come back. It would only go through in one direction. Now, that'd be an unusual piece of glass, wouldn't it? Imagine you have a glass or a crystal or a piece of material that's clear, and you shine a laser beam through it, and as the light passes through, it rotates the polarization of the beam. It changes some quality of that laser beam. And it's in a measurable way, a way that can affect things. Data is being stored this way, and it was done a lot more in the past on devices called magneto-optical drives. So somehow, using magnetism, you change a property of light. And this was used for storing, erasing, and rewriting data for computers when the density of most storage media was not very high. Floppies were around. They only store a couple of megabytes, 1.5 megabytes or so. But a magneto-optical drive could store a couple of gigabytes in comparison. So you can imagine there was a lot of desire to go to a much higher density format, and it was for a while used as basically an archival or backup drive. These were much more popular in Japan than in the US, but they've kind of fallen out of use. Nevertheless, the effect is very useful because it can also be used for works in nanotechnology. So let's talk about the Faraday effect and the magneto-optical name and what it all leads to. So Michael Faraday was one of those amazing polymath individuals who worked in electricity and chemistry, made some of his own batteries, made interesting compounds. He worked with magnetic fields and motors, and he made the first practical, or I should say impractical, electric motor, which was little more than a pool of mercury at one pole and a wire hanging down at the other with a magnet in the middle. And the wire, like a wand, was dipped in the mercury, and it would swing around and around in a circle when he applied a current to it. It couldn't do anything other than that, but it was proof that the electrical current could be used to move something, and that was the first time that had really been done in any practical manner. Then they experimented with things such as the needles of a compass and magnetism in wires, loops of wires, and solenoids. And they were able to prove that magnetism and electromagnetism were two different faces of the same force. But now we're looking at light itself. Well, Faraday noticed when he had a certain clear crystal of material, and it was near a solenoid, a coil, that a magnetic field is generated by, when light would shine through the material and he applied a current, it would change the polarization of the light and how much light would get through the crystal. Well, this was a very interesting effect, and he was interested in proving that all the forces of nature were tied together somehow or other. And it was it was a laudable goal. It isn't entirely correct, but he was close enough that he was able to get some experimental results that were very interesting. Later on, they created a device based on this principle called the Faraday rotator. Now, there's a special class of garnets, and garnets are semi-precious gemstones, a special class of garnets that will take laser light, and because of quantum mechanics and the way polarization works, it acts like two signals impressed on each other create a rotation effect. And the effect is the phase of the light wave is being changed in some way that makes it rotate. Now, when this happens, you find that you actually can apply a current and vary the light wave in a certain rotation and actually get a measure of the current. So a Faraday rotator is a device that when you apply power to it, light passing through it gets rotated. Now, what does that mean, rotated? Well, you know how light is supposedly a wave under most circumstances that we would normally see with our eyes. And that light is waving up and down along some axis. Now, there are actually two signals in light. There is an electrical field oscillating in one direction and a magnetic field operating at 90 degrees to it. And those two fields welded together are what creates light, or is the substance of light, would be more accurate. When a light wave is moving through a material that is affected by a magnetic field, it shifts the magnetic field of the wave and therefore of the light. It changes the direction that the light is oscillating. This is polarization. So imagine the light waves are going like this, and you have slots that are lined up with it, and the light waves can get through. What happens if you turn the slots? Less and less light gets through until extinction. It can't get through. This is polarization of light in a sense. The polarization is determined by where the magnetic field and electric field are lined up relative to the travel of the light wave. Now, Polaroid sunglasses have materials in them, in a plastic usually, and that material can do one simple task, and that is align the polarization of light in one direction. It's known that light reflecting off the surface of water and other shiny materials reflects in a certain direction only. Well, the glasses are 90 degrees to that to cut out the blur, the brightness and the glare. And this is what Polaroid sunglasses, or polarized sunglasses in general, do for you. So you also will notice that when you look at a cell phone or a computer screen these days, and your sunglasses are on and you turn them, you'll see the screen get lighter and darker. What's happening is the alignment of your glasses is going at odds with the alignment of the polarized light in the display of a cell phone or of a computer monitor. And people had to take this into account when devising these displays. They knew the direction of polarization of sunglasses had to be a certain thing because of the reflection surfaces of water. So they had to design computer video displays and phone displays to be in the proper polarization to match your glasses. Why is this important? Polarized light can be used for a number of things, and one of them is if you have two polarizers, one over a source of light and one behind, let's say, a clear piece of plastic, the light will show colors in the plastic when you stress or flex it or pull it. You can actually see where the most or least stress happens in the piece of plastic. Now, engineers used to use this as a trick to measure how much stress was on the design of a mechanical part. They would cut out a clear plexiglass piece shaped like their part, and then they would stretch it and push it and pull it applying force to the most delicate parts that they could figure the damage would be the greatest under stress. By looking with polarized light and polarized glasses, they could literally see the lines of distortion in the plastic and determine where it had to be made stronger and then where they could get away with removing material. So polarized light was used often in stress analysis and to help design components. But in computer data, how do you store data with polarization? Well, that's actually very simple. Data is often written with a magnetic field. And in hard drives, typically we have a mechanical system with a disk spinning, and that disk is coated with a magnetic coating. There's a tiny read and write head, and it is literally a tiny magnetic loop. And when the disk is writing information, that head is being used to set the direction of the magnetic field in the spinning disk in tracks, circular areas storing a ring of data. So billions of bits of data can be written on a disk this way, but normally it takes a stack of small disks inside a hard drive to have the space to write all of those bits. With the magneto-optical effect, you can write the magnetic field and you can read it with a laser. And the laser shines against a section of the disk and catches the reflection. Where the magnetic field comes in is this. The polarization of the laser light is known, and if it matches that of the material where the data is written, it will reflect the light back toward the source. If the polarization has changed because the magnetic field is written there, like a 1 instead of a 0, then the light will not reflect back toward the laser, or it will be greatly diminished. And this is easy to read. So you can write it with a magnetic head and read it very quickly with a laser, a non-contact technology. Nothing rubs, nothing touches, and nothing wears out. So it's actually a very fascinating concept that you can use a magnetic field to change the properties of materials. Now, this has also been used to make glass that can change color, polarization, or become almost like a mirror on command. Various types of materials, particularly, as I said, garnets, are used to do this. And there's a general chemical formula for this type of garnet. A rare earth element is involved in this, and that's something like neodymium or yttrium or ytterbium, strange, odd names for elements at erbium that you may never have heard of before. Rare earth elements aren't actually that rare, but it's something that in times past had little or no use and was sometimes hard to find. Scandium, weird element names like that. Well, the formula is R3Fe5O12, where R is the number of elements of rare earth material. So you'd have three atoms of a rare earth element such as scandium, and then 5 atoms of iron, and 12 atoms of oxygen, all put together in a specific crystal form that makes this semi-precious gem the garnet. When the garnet has the magnetic field applied to it, it will change the polarization of the light passing through it. So it's an easy enough thing to understand, and many different varieties occur. It blocks the reflection of laser light back toward the laser when the field is applied, and it changes its polarization. So the Faraday effect also had a second name, and he discovered this effect in 1845, I think I might have mentioned. When he discovered this, it was often referred to as the Magneto-optical Faraday effect, MOFE. And one of the more common materials used to illustrate it is called terbium gallium garnet. And gallium is another one of those strange materials. Gallium is a metal that's solid at room temperature, but it will melt at the heat of the palm of your hand into a material very much like mercury. It's often used to make things like trick spoons where you stir it in the coffee and the spoon melts. But it does have plenty of interesting uses in semiconductors and in this case, optical devices. So, magneto-optical effect, one of those interesting things that we were aware of a century and a half or more ago, discovered by one of the greats of electrical and chemical work, Michael Faraday, and ended up being one of our means of storing archival data a while back. Now you don't see it as much, but it still has other use, as I mentioned, in nanotechnology. It's possible to make arrays of quantum dots which are each tiny light emitters. They can be normal LED or even laser type light emitters. And they're extremely tiny and work on quantum mechanical effects. Arrays of these quantum dots can be put together with a magneto-optical crystal and make some very interesting quantum type displays and other devices, memory devices. We're just exploring some of the things that these devices will do. We expect it'll improve our means of putting data in and out of new exotic systems, possibly in quantum mechanical systems. And we also know that it can be made into extremely interesting and effective display technologies. Much of the display technology we're working on today leads toward that holy grail, holographic displays. And my understanding is by combining the polarization of light on arrays of quantum dots, it may be possible to make devices that literally make those displays that appear to float in air. So, something that started with a coil of a solenoid and a piece of a garnet with Michael Faraday in 1845 leads all the way up to the possibilities of making holograph type displays, 3D displays that appear magically in the air, using these crystal devices as the source of polarization of light. Now, if anybody has any questions about magneto-optical devices, the floor is open. In the meantime, I'm going to do my sales pitch. Please come to schultzlaboratories.com or universesciencecenter.com, sign up as a member, join our classes, help our galleries grow and increase in number, and increase the number of interactive displays we have. If you want to be an educator in your own right, and you want to do it in a virtual world that can reach millions of people all over the world through the internet, contact us and we can put a virtual gallery together for you, or we can put a classroom together for you, or both. So if you want to teach anything from how to paint a car, how to make a semiconductor, how to cut hair, how to draw a picture, it's all up to you. Well, no questions have arrived on the floor, and I'm going to read my quote for the day. And it is, "Every moving thing that lives shall be food for you. I have given you all things, even as the green herbs. But you shall not eat flesh with its life, that is, its blood." And that's Genesis 9:3 and 4. I guess there are no restrictions on my diet, really. Anyway, I hope you've enjoyed the commentary on magneto-optical devices and effects. And you can look up a lot of material on Wikipedia. There's quite a bit of material there you can use to make experimental devices yourselves. And by the way, rotating laser beams comes to an effect called the Pockels cell. They used to make lasers, and they sometimes still do, that could build up their energy in a reflective cavity, and then on command, this rotator, this Pockels cell, would swap polarization and open up like a floodgate, and all the energy would come out in one burst. Fascinating thing. Imagine filling a water balloon and then popping it. Well, that was the same effect, but with a laser light. Well, everybody, have a wonderful evening. This is the Randomizer, and I hope you'll join us tomorrow at 6 p.m. Eastern Standard Time. Join us live, bring us your questions, comments, and ideas, and we'll put you on the air live to talk to everybody. And thank you for watching tonight, and as usual, make the world a better place. I'm Charles Schultz, and thank you for joining us.